Problem 3. For the radial network shown in figure, a three-phase fault occurs at point F. Determine the fault current and the line voltage at 11 kV bus under fault condition. Choose 100 MVA 33 kV as base. See, this is a given power system, single line diagram of the given power system network. We have 11 kV bus. This is 11 kV bus written as 11 kV, to which two generators G1 and G2 are connected, and the ratings of the generators are given. Followed by the 11 kV bus, we have a transformer T1, a step up transformer, and one more transformer T2, a step down, whose ratings are given. And in between T1 and T2, we have an overhead transmission line of 30 km, whose impedance is 0.27 plus j0.36 ohm per kilometer. So for 1 kilometer, the impedance is this. So for 30 kilometers, you have to multiply this value by 30. 0.27 plus j0.36 into 30 will give you the total impedance of this 30 kilometer transmission line. So the secondary of the transformer T2 is going to a cable, feeder cable, which is of 3 km length, and the cable impedance is also given on per kilometer basis. So after 3 km length of the cable, there occurs a fault F. You can write here as F fault F. Okay. And the main difference of this problem compared to the other two problems are, see, in the first two problems, a generator and a motor in between a transmission line or a transformer. Okay. So the motor will be the load for the generator. So those two problems are generator under loaded condition. The load is the motor and the fault occurs at the motor terminals. But in this problem, if you see, the generator side is terminating in a fault. Okay. And they have not mentioned about the load here. So it means this point where the fault occurs, it is an unloaded point. The generator is unloaded. Okay. So actually the procedure is, if the machine is unloaded, the pre-fault voltage should be considered as 1 per unit. Note it. This I have not given in the procedure notes, whatever I have scanned and forwarded. So if the system is unloaded, take the pre-fault voltage as 1 per unit. Okay, so that is one main difference. Then the other differences are, we have transformer. So if there is a transformer and different rated machines and given 100 MVA 33 kV as the base, based on the transformer, we divide the network into different sections. So in each section, you have to find the new base values, as we have dealt in module 1. Okay, so that is the one more difference for this problem. So now, with respect to T1 and T2, I divide the given power system network into 3 sections. So the incoming generator till transformer 1 primary is section 1. The overhead transmission line 30 km is section 2, and from the secondary to the fault occurrence point is section 3. Okay. So now let's go for step 1. So what is step 1? Choose appropriate base value and to draw the pre-fault impedance diagram. So let us choose appropriate base value. So given in the problem, to select 100 MVA 33 kV as the common base. Okay. So 100 MVA 33 kV common base. But they haven't mentioned in which section it has to be considered. See, I have considered this base value with respect to transmission line section, that is section 2, because in section 2 only we have the transformer rating, secondary of this transformer and primary of this transformer is 33 kV. So I have considered this common base with respect to the transmission line section, that is section 2. So now, as we have done in module 1, we can calculate the new KVB values for section 1 and section 3. Okay. So hope you all understood why I have written the base value. It's given in the question and I have taken it with respect to section 2. So now let us find the new base values in section 1 as well as in section 3. So for section 1, you know, the MVA remains the same, 100 MVA. Okay. So KVB is, see, listen here, we are moving from section 2 to section 1. Okay. So 33 is the base kV in this section into 11 kV by 33 kV. So which will give you 11 kV as the new base for section 1. In the same way, you calculate the new KVB for section 3. KVB is equal to 33 into 6.6 by 33. 2 section divided by from section. 6.6 by 33, which will give 6.6 kV. Okay. So now to draw the pre-fault impedance diagram, you need to calculate the new values of the reactances of various components. All the components are given with the old per unit reactance. Since we have the new base value in the respective sections, you have to calculate the new reactance value. So this is the procedure we have used for so many problems in module 1. So generator 1 new reactance xg1 new is equal to xg1 old into MVAB new by MVAB old into KVB old square by KVB new square. So what is xg1 old? 0.15 into MVAB new in section 1. Generator 1 comes in section 1. 100 divided by what is the generator 1's old MVB? 10 into, so what is the KVB old of generator 1? What is KVB old? 11, because it is connected to 11 kV bus. So the generator rating is also 11 kV divided by what is KVB new in that section 1? 11. Okay. So you will get xg1 new is equal to J1.5 per unit. Okay. So now we have to calculate xg2 new. What is xg2 new? xg2 old, which is 0.125 into what is MVAB new for section 1? 100 divided by what is MVAB old of generator 2? 10 MVA into KVB old by KVB new. KVB old is 11 kV, new is 11 kV. Okay. The same way, calculate for XT1. XT1. What is the old value? J0.1 into what is the new value of MVA? 100 divided by old MVA 10 into, with respect to primary side, let us consider 11. Primary falls in section 1. So old is 11 kV. Old is 11 kV. New is also 11 kV. Okay, so you'll get J1 per unit. In the same way, find XT2 new. For transformer 2, old is 0.08 into new MVA 100 divided by old MVA 5 into, with respect to primary, we can take 33 by 33, or with respect to secondary, if you take it is 6.6 by 6.6, which will give J1.6 per unit. Okay. But coming to the 30 kilometer transmission line, Z line, and coming to the 3 kilometer cable, Z cable, the values are given in ohms per kilometer. The values they had given in ohm per kilometer. So we have to find in per unit. And what is the formula in per unit? Actual divided by base. Z line per unit is equal to Z line actual divided by Z line base. So what is Z line actual? 0.27 plus J0.36 ohm per kilometer. That is the reason why I have multiplied by the length of the overhead line, which is 30. Okay, so 0.27 plus J0.36 into 30. So be clear why I have substituted this 30. So it is to get for the entire 30 kilometer length of the overhead transmission line divided by base value of impedance is KVB square divided by MVAB. Those two are new values. What is KVB new in section 2? 33. What is MVAB in section 2? 100. So on calculating you will get this value. So in the same way, find the impedance of the 3 kilometer cable, actual by base. So for 1 kilometer it is 0.135 plus j 0.08. For the entire 3 kilometers, multiply by 3 divided by KVB square by MVAB. So now in which section cable, 3 kilometer cable belongs to? It belongs to section 3. So what is the KVB new in section 3? It is 6.6 kV. So 6.6 whole square divided by MVAB. So this you should be careful about. The cable falls in section 3. So we have taken the KVB new of KVB of section 3, which is 6.6. So on calculating we will get the value in per unit. So now with the new per unit values, you draw the pre-fault condition impedance diagram. Okay. See two generators connected in parallel, XG1, XG2, EG1, EG2. See, notice that in the problem they haven't mentioned whether it is subtransient or transient or steady state. So in general we are finding. Okay, so I have not put double dash. If you put double dash also, nothing wrong in it. Okay, so two generators in parallel followed by, this is the 11 kV point, 11 kV point. So this is the 11 kV point. Okay, then XT1 we have found. This is impedance of the 30 kilometer OH line. This is XT2 impedance of the cable. So at the end of 3 kilometer cable we have a fault. We have a fault. Okay. So listen here. I have written V pre-fault is equal to 1 per unit. Why? Because the generator is, the system is unloaded. Okay. So for unloaded system, consider the pre-fault voltage as 1 per unit. Okay. So that is what step 2 says. What is step 2? We have to find the pre-fault voltage at the fault point, and we have to calculate the load current. Okay. So here there is no load on the system. Hence the system is unloaded prior to fault occurrence. So hence assume pre-fault voltage is 1 per unit. Okay. So let us solve this problem by using Thevenin's method. We can solve by other method also. So in the first two problems I have told about both the methods. Here we will solve only by Thevenin's method. So what does Thevenin's method procedure say? Step 2. The pre-fault voltage is the Thevenin's voltage VTH. Pre-fault voltage is the Thevenin voltage VTH. So I have written VTH is equal to V pre-fault is equal to 1 per unit. Understood? So now go to step 3. So what is step 3? We have to find ZTH. We have to find Thevenin impedance at fault location. Okay. So what you have to do? You have to short circuit the voltage sources, which is EG1 and EG2. I have shorted. Okay. By shorting the voltage sources, I have redrawn the reactance diagram, which all the reactances and impedances. And what is ZTH? It is the looking back impedance from the fault point, at the fault point FO. So now if you look on to this J1.5 and J1.25 are in parallel in series with all the other impedances and reactances. Okay, so these two are in parallel. The parallel combination of these two is in series with the remaining all reactances. Okay, you will get the value like this. Now step 4. Thevenin's equivalent circuit at fault point. Okay, so how to draw the Thevenin's equivalent circuit? VTH in series with ZTH and represent the type of fault at the fault terminal. So have they mentioned about the type of fault? No. So we have considered as a short circuit fault occurring at fault terminals FO. So what is this point actually? It is the feeder after 3 kilometer length. Fault occurs at the feeder after 3 kilometer length. Okay. So now what is fault current? By simple KVL, IF is equal to VTH by ZTH. You got this. Understood? And now you have to calculate the actual value of fault current. IF actual is equal to IF per unit into I base. So we have to calculate the I base. What is I base? Formula for I base is KVAB by root 3 into KVB. Okay. So here while substituting the values of base, be careful. You have to take the section 3 values alone because the fault has occurred in section 3. The fault occurrence is in section 3. So substitute for section 3 base value. So how can you write KVB? KVB is nothing but MVAB into 1000 divided by root 3 KVB. So on substitution you will get the value. Now find out IF actual. IF per unit into I base. Okay. So this is the fault current. So apart from the calculation of fault current, they have asked to calculate one more data. What is it? They have asked to calculate the line voltage at 11 kV bus under fault condition. The line voltage at 11 kV bus under fault condition. Okay. So from the fault point, go backwards. From the fault point till the 11 kV bus. From fault point till 11 kV bus, calculate the total impedance. Go back to pre-fault condition impedance diagram. See, this is the fault point. This is the 11 kV bus. So the impedance from the fault point till 11 kV bus is XT1 plus Z line plus XT2 plus Z cable. XT1, yeah, or we can go in the reverse direction. Yeah, this is XT1 plus Z line plus XT2 plus Z cable. Okay. So which is Z till the 11 kV bus. Now fault current in per unit already we have calculated from step 4. Okay. So now voltage at 11 kV bus is equal to impedance till that point into IF. Voltage is equal to Z into IF. Okay. So impedance I have substituted, IF I have substituted, you got the answer in per unit. Now the actual value is per unit value into base value. Okay. So what is the per unit value? Already calculated. Into what is the base value? 11 kV. So the bus is in 11 kV bus is in section 1. 11 kV bus is in section 1. So consider the base voltage of section 1, which is 11 kV. So 9.625 angle minus 2.82 kV. Okay. So since they have asked to calculate the voltage at 11 kV bus under fault condition, take the impedances from the fault point till the 11 kV bus. This impedance. Okay. Then fault current already we have calculated. The usual formula, voltage in per unit. Then for finding out the actual voltage, multiply the per unit voltage into base value. So here should be very careful. You should take only for section 1 because 11 kV bus is in the section 1. So 11. So 9.625 angle minus 2.82.